Hello again. So today we're going to be talking about the chain rule. The chain rule is, there's a couple ways to write the chain rule. One way to write it is dy dx equals dy du times du dx. Okay. So they could give you a problem where you sort of want to use the rule this way. I've seen some problems where they like describe y as a function of u, and then they describe u as a function of x. And then you sort of take those two derivatives, multiply them together. But the more common way we're going to be using the chain rule is it's used when you have a composition of two functions. And it's not so obvious the way the chain rule is written right here that is what the chain rule is good for. So the other way to write the chain rule, which is this, the derivative with respect to x of f of g of x is the derivative of f of g of x times the derivative of g of x. So this is a derivative rule that we're going to use whenever you have a composition of two functions. If you don't remember what a composition is, it's when you take one function and put it inside of another function. That's called a composition. Okay, so the chain rule could be called the composition rule, but they call it the chain rule. Anyway, so and even written this way, it may be a little bit confusing as to exactly what's going on. So the best way to sort of learn the chain rule or to get accustomed to it is just by looking at some examples. So let's go ahead and look at some examples of the chain rule in action. Okay, so what if we had the derivative of e to the power of x cubed? Maybe to make it a little bit more clear, that the x cubed is entirely up on top of the e, I'll put in parentheses like that. Okay, so what is the derivative of this? Okay, basically this is a composition of x cubed has been put inside of the function e to the x. Okay, the outermost function is that e to the x function, and that's what we want to take the derivative of first. Well, the regular derivative rule for e to the x is just e to the x. So we just start off by leaving it alone. And then you have to multiply by the derivative of the inside function, in this case, the derivative of the top. So the derivative is going to be e to the x cubed times 3x. You can generalize this for this rule for exponents, that whenever you have the derivative of e to any function f of x, the derivative is going to be e to the f of x times the derivative of f of x. You could say this is the chain rule version of the regular derivative rule for e to the x. Okay. Let me switch this around. Instead of that, what if we were taking the derivative of e to the x in parentheses cubed? Okay. Now there is an alternate way of writing this, but I want to keep it like this and explain how to take the derivative the way it's currently written. So this is the function e to the x has been put inside of the function x cubed. It's the opposite order of this one. Since x cubed is the outer function, that's what we have to take the derivative of first. And our derivative rule for x cubed is 3x squared. You know, you bring down the power, reduce the power by 1. So bring down this power, reduce the power by 1. But you keep what's inside the same, this e to the x. Then you multiply by the derivative of the inside, so the derivative of e to the x, which is e to the x. So that's going to be our answer. Now I know there's another way that we could have simplified this. When you raise something to a power and then to another power, you can multiply the two powers. So we could have written this as e to the 3x. And if you take the derivative of it written this way, you know, using that rule, we get e to the 3x times 3. This is the same as this because e to the x squared reduces to e to the 2x times another e to the x would be e to the 3x. And there's the 3. So you see we get the same answer. Okay, so you can generalize this rule to be whenever you have the derivative of any function raised to the nth power, you bring down the power, reduce the power by 1, and then multiply by the derivative of the inside. Some textbooks call this the general power rule, but it's really just an application of the chain rule. Okay? So let's do one or two more examples. Oh, I know a better one. Let's do the derivative of secant of x squared plus x. Okay, I chose this one because the derivative of secant is secant x tangent x, and that formula has two x's in it, so you have to be a little bit careful when you're doing this derivative. Okay, so the derivative of the outer function, secant, is secant x times tangent x. But when you're doing the chain rule, you know, you replace this x with whatever's inside here, keeping it the same. So we have to replace both of the x's in the regular formula with x squared plus x, and then times the derivative of the inner function. So the derivative of x squared plus x is 2x plus 1. There, and that's the derivative. So you do have to be a little bit careful whenever your basic derivative function has x's in multiple locations. You're going to have to fill them in with whatever f of x is. So once again, you know, we can write a general rule when you have secant of f of x. The derivative is going to be secant f of x times tangent f of x times the derivative of f of x. Okay, now the chain rule can be used in the middle of other rules. Like you might have a problem that involves both the chain rule and the product rule, or the chain rule and the quotient rule, or maybe even all three of those, which would be very annoying. Let's do one example of that. Let's do the derivative of x times sine of 2x over e to the power of 2x. Okay, so what rule do we apply first? Well, the whole thing is a quotient, so we should apply the quotient rule first. Basically, when you're applying derivative rules, the order that you need to apply them is basically, if you were evaluating this as a number, what is the last mathematical operation you would do? You know, you'd work out the top, you'd work out the bottom, then you divide them. The division is the last operation. So that's the first operation you have to do when you're applying your derivative rules, is whatever is the last operation. Okay, so quotient rule. And that is the derivative of the top times the bottom minus the top times the derivative of the bottom, all over the old bottom squared, which would become e to the 4x. Okay, now we'll work out these two derivatives. This derivative, it's a derivative of a product, so we have to apply the product rule. Okay, derivative of the first is 1 times the second plus the first. Then we come to the derivative of sine of 2x, and that's a chain rule. Now the derivative of sine is cosine, so we get cosine of 2x. Then we have to multiply by the derivative of the inside, so times 2. Okay? And that completed that product rule. Okay, and that product rule is times this, so let's put a big parentheses because the whole thing is multiplied by e to the 2x, and then minus x sine 2x times, and then the derivative of e to the 2x, that's yet another chain rule. It's going to be e to the 2x, then times the derivative of the top, so it's e to the 2x times 2. And all divided by e to the 4x. Okay, and then let's try to simplify this as much as possible. One thing I would notice is that we have an e to the 2x here, an e to the 2x here, and an e to the 4x at the bottom. So we can divide by e to the 2x everywhere on the top and the bottom. That's going to get rid of these two, and that's going to reduce this down to e to the 2x. Okay, and now let's clean up the rest. We have 1 times the sine of 2x plus 2x cosine 2x minus 2x sine 2x. All over e to the 2x. Doesn't look like there's anything more that I can do to simplify that, although maybe some people might group these two together because they both contain a sign in them. So maybe it might be written as 1 minus 2x in parentheses times sine 2x, that's grouping those two together, and then plus the 2x cosine 2x. Okay, and that would be the final answer. All right, so that's going to be the last example of the chain rule for now. Now, it turns out that the chain rule is useful in a lot of different ways. There's a lot of different ways you can apply the chain rule. There's implicit differentiation. There's deriving the inverse trig functions, the derivative rules for the inverse trig functions, and related rates. And there may even be some more examples. I'm just forgetting off the top of my head right now. But that's what we're going to be exploring in the next couple of videos, is some of those applications of the chain rule. Okay, so that's going to be it for this video. Hope you have a good day.